Modern software systems are often very complex. They don't run on just one computer anymore. Instead, they are distributed across many machines. These machines need to work together seamlessly. This coordination can be incredibly challenging. The CAP theorem provides a crucial understanding. It helps us build better, more reliable distributed systems. So what is this CAP theorem? It was first presented by computer scientist Eric Brewer in 2000. The theorem states a fundamental truth about distributed data stores. It says a distributed system can only guarantee two of three properties: consistency, availability, and partition tolerance. You cannot have all three perfectly, all the time. This might sound a bit like a riddle at first, but it's a very practical guide for system designers. It forces us to make important choices early on. Two other scientists, Seth Gilbert and Nancy Lynch, later proved it formally. This means it's a fundamental constraint, like a law of physics for these systems. Understanding this theorem is vital for anyone involved with large-scale software. It helps manage expectations about what a system can truly deliver. Let's begin this journey into distributed system realities. Let's start with C, which stands for consistency. In the world of CAP, consistency means something very specific. It means that all clients see the same data at the same time, no matter which node in the distributed system they connect to. If you write a new piece of data, that data becomes visible. Every subsequent read operation will return that new data. This is often called strong consistency or linearizability. Imagine you are editing a shared document online with a colleague. If you type a sentence, consistency means your colleague sees it immediately, exactly as you typed it, without any delay or old versions. Consider another example, your bank account balance. When you withdraw money from an ATM, you expect your balance to update. If you then check your balance on your banking app, it should show the new, lower amount. If the app showed the old balance, that would be an inconsistency. Financial systems heavily rely on strong consistency. They need to ensure that every transaction is accurately reflected. Consistency, therefore, is highly desirable for many applications. It makes the system behave predictably from a user's perspective. However, achieving strong consistency in a distributed system can be costly. It often involves complex coordination protocols between nodes. This can impact performance and availability, as we will see. Next up is A, which stands for availability. Availability means that the system is always operational. Every request made to the system receives a response. The system doesn't just go silent or return errors frequently. It's always ready to serve requests from users. Importantly, this response doesn't have to be the most recent data. The system prioritizes being responsive over having perfectly current data. Think about your favorite social media platform. You expect to be able to open the app or website anytime. Even if some background servers are having issues, the platform should still work. This is a hallmark of a highly available system. It prioritizes user access and interaction above all else. Another example is a large e-commerce website like Amazon. During peak shopping times like Black Friday, millions of users access the site. The website must remain available to take orders. If the site goes down, the company loses a vast amount of sales. So these systems are designed for extreme availability. Availability is crucial for businesses that rely on constant user engagement. However, as CAP theorem suggests, this focus on availability can come at a cost. Specifically, it might mean sacrificing strong consistency. This is a trade-off that system designers must carefully consider. Finally, we have P, which stands for partition tolerance. A partition in this context refers to a network partition. This happens when communication breaks down between different parts of a distributed system. Imagine your system has servers in different data centers. If the network cable connecting these data centers is cut, a partition occurs. The servers in one data center cannot talk to the servers in the other. Partition tolerance means the system continues to operate despite such breaks. It doesn't grind to a halt or completely fail. Consider a global online service like Google Search or Gmail. Network issues between these data centers are not uncommon. Despite these partitions, you can still usually access Google Search. You can still send and receive emails via Gmail. The system is designed to be partition tolerant. Different parts of the system might operate independently for a while. They then reconcile any differences once the network link is restored. Think about a mobile application that needs to sync data with a server. Your phone might temporarily lose its internet connection. A partition-tolerant app might allow you to continue working offline. This ability to function despite network issues is partition tolerance. It makes applications more robust and user-friendly. Section 5. The crucial role of CAP theorem in modern distributed systems. The CAP theorem isn't just an abstract academic concept, it plays a crucial role in how modern applications are built and behave. Today, almost every significant application is a distributed system. Think about cloud computing platforms like AWS, Azure, or Google Cloud. Think about microservice architectures where applications are broken into smaller, independent services. All these rely on multiple computers communicating over a network. This inherent distribution makes them subject to the CAP theorem's constraints. Understanding CAP is therefore essential for building reliable software. The theorem provides a vital framework for system architects. It forces them to think critically about their system's priorities. What is more important for this particular application? Is it absolutely critical that all users see the exact same data instantly, or is it more important that the system is always up and responsive? These are not easy questions, and the answers vary. The CAP theorem doesn't give the answer, but it clarifies the trade-off. It helps architects make conscious, informed decisions, rather than discovering these limitations through painful failures later on. This proactive approach leads to more robust and predictable systems. The challenge of scale further emphasizes CAP's importance. As systems grow to serve millions of users and handle vast amounts of data, they become more distributed. This increased complexity also increases the probability of network partitions. Section 6. The inevitable trade-offs CA, CP, and AP systems. As we've seen, partition tolerance, often abbreviated as P, is often non-negotiable in distributed systems. Networks are inherently unreliable, messages can be lost or delayed. So if we assume P must be supported, the CAP theorem says we must choose. We must trade off between consistency, C, and availability, A. This means that during a network partition, a system can either choose consistency over availability, making it a CP system, or choose availability over consistency, making it an AP system. It cannot provide both perfectly when nodes are unable to communicate. This choice defines the system's behavior during failures. Let's explore these combinations. First, let's briefly touch upon CA systems, which combine consistency and availability. A CA system chooses to provide both consistency and availability. According to the CAP theorem, such a system cannot tolerate partitions. In practice, California systems are typically traditional, single-site databases. Think of a relational database running on a single, powerful server. As long as that server is up and there are no internal partitions, it can be consistent and available. However, these systems are not inherently designed for distributed environments where partitions are common. If you try to distribute them without careful design, they might struggle with P. So, California is often associated with non-distributed or tightly coupled systems. Next, consider CP systems, which combine consistency and partition tolerance. Section 7. Real-world choices. Examples of CA, CP, and AP in action. Let's look at how these CAP choices play out in real-world systems. Traditional relational databases like single-instance MySQL, PostgreSQL, or Oracle often aim for CA. When running on a single server, they provide strong consistency, often referred to as ACID properties, and high availability, as long as the server is up. They are not inherently designed to be partition tolerant in a distributed sense. While you can set up replication or clustering, handling network partitions between replicas often requires careful configuration. These configurations might lean towards CP, blocking updates if replicas can't sync, or risk AP, allowing divergent data. For many applications with centralized data needs, this CA model works well, but it becomes challenging when scaling out globally. CP systems, which combine consistency and partition tolerance, are chosen when data integrity is absolutely paramount. Think of financial systems like those managing bank transfers or stock trades. An error or inconsistency here could have severe consequences. During a network partition, these systems would rather stop processing some transactions, reducing availability, than risk an inconsistent state. Examples of technologies that can be configured as CP systems include HBase, MongoDB with specific read-write concerns, or distributed consensus systems like Zookeeper or etcd. Google's Spanner is a notable example aiming for strong consistency at a global scale, making careful trade-offs. These systems ensure that even if parts are disconnected, the data remains trustworthy. AP systems, which combine availability and partition tolerance, are very common for large-scale web applications. Consider Facebook's social graph or Twitter's feed. It's generally more important that users can access the service and see something, even if it's slightly outdated. Section 8. Modern applications. Applying CAP principles today. Modern applications often don't rely on a single monolithic database or system. Instead, they are frequently built using a microservices architecture. Each microservice can have its own data store, chosen specifically for its needs. This allows for a more nuanced application of CAP principles. For example, an e-commerce application might use a CP database for order processing and payments. Here, consistency is critical to avoid overcharging or losing orders. Simultaneously, it might use an AP system for product recommendations or user reviews. For these features, high availability and responsiveness are more important than immediate consistency. Seeing slightly stale recommendations is usually fine. A common pattern in AP systems is eventual consistency. This model acknowledges that data might be temporarily inconsistent across replicas during and after a partition. However, it guarantees that if no new updates are made to a given data item, all replicas will gradually converge to the same value. The system works in the background to propagate changes and resolve conflicts. This is a practical compromise that allows for high availability and partition tolerance. Many NoSQL databases are built around this model. It requires application developers to be aware that reads might not always return the absolute latest write. They need to design their applications to handle this possibility. The decision of where to position an application or service on the CAP spectrum depends heavily on business requirements. Section 9. Conclusion: Making informed choices with CAP. To wrap up, let's quickly recap the essence of the CAP theorem. It states that any distributed data store can only provide two of these three guarantees simultaneously. Consistency, meaning all clients see the same data at the same time. Availability, meaning every request receives a response. Without guarantee, it's the most recent data. And partition tolerance, meaning the system continues to operate despite network failures between nodes. This isn't a guideline, it's a fundamental limitation proven mathematically. It forces designers to make conscious decisions about their system's behavior, especially when faced with the realities of distributed computing. In most modern distributed systems, network partitions are considered inevitable. As systems scale out and become more geographically dispersed, the likelihood of communication failures increases. Therefore, partition tolerance P is usually a mandatory requirement. This means the primary trade-off for system designers is between consistency C and availability A. When a partition occurs, do you prioritize ensuring all data is perfectly consistent, potentially by making parts of the system unavailable, which is CP? Or do you prioritize keeping the system responsive to all users, even if it means some might see slightly stale data, which is AP? This choice is at the heart of distributed system design. It's crucial to understand that there is no universally correct answer in the CAP dilemma. The best choice depends entirely on the specific requirements of the application. For a financial ledger, strong consistency is paramount. For a social media feed, high availability is often preferred. The CAP theorem empowers architects and developers to understand these trade-offs. It allows them to make informed decisions that align with business goals and user expectations. By acknowledging these inherent limitations, we can design systems that are more resilient. We can build systems that behave predictably, even when faced with network problems. The CAP theorem, first articulated by Eric Brewer, remains a cornerstone of distributed systems theory and practice.